In this video, we're going to introduce the idea of a partial fraction decomposition of a rational function. This will be an algebraic tool that is used to rewrite a rational function in a simpler way, which will allow us to integrate it more easily. To illustrate how this method is useful in evaluating integrals, let's consider the integral of the rational function x plus 5 over x minus 1 times x plus 2 dx. As written, there's really not much we can do with this integral. There's no way to make a u substitution or use integration by parts or any other technique that we've seen in order to integrate it. However, if we observe that this rational function can be rewritten as the sum of two simpler rational functions, in particular in this case, we could rewrite this as 2 over x minus 1 minus 1 over x plus 2. We could check this by just simply subtracting on the right-hand side and see that we will obtain the original rational function. Once we've seen how to rewrite our rational function in terms of simpler rational functions, we can replace the integral of our original rational function with the integral of the difference of our two simpler rational functions, as seen here. This new integral is easily computed since each term has an antiderivative involving a natural log. For example, our first term, the antiderivative would be 2 times the natural log of x minus 1 in absolute value. And our second term will have an antiderivative of the natural log of x plus 2 inside an absolute value. And of course, plus our arbitrary constant c. And so this blue step here, this blue decomposition, being able to rewrite this rational function in a simpler way as a sum or difference of two simpler rational functions, allows us to rewrite our integral into a different form, which is easily computed. The idea behind partial fraction decomposition is to go from our original rational function and decompose it into a sum or difference of simpler rational functions. And so the process for doing that is what we will be discussing next. When trying to find the partial fraction decomposition for a particular rational function, the first thing that we need to do is to check that the degree of the numerator is actually smaller than the degree of the denominator. This will mostly be the case, but if it's not, we do need to use polynomial long division in order to make it so. The rest of these steps will only apply to rational functions whose numerator has a smaller degree than the denominator. Once we ensure that the degree of the numerator is smaller than the degree of the denominator, we're going to factor the denominator completely. Now, by a fact of polynomial algebra that you've seen before, every factor of our polynomial in the denominator will either be a linear factor, which means we can write it in the form x minus a for some real number a, or it could be a quadratic factor, which means we can write it in the form x squared plus bx plus c. If we have a factor that has a higher degree than 1 or 2, like linear or quadratic factors, then that means we can still factor it more. So every factor will always have a degree 1 or a degree 2, and so will be linear or quadratic, respectively. We now consider each factor of the denominator one by one. For each linear factor in the denominator, so any factor of the form x minus a, we're going to add to the partial fraction decomposition the sum shown here. Specifically, a constant a1 divided by x minus a, plus another constant a2 divided by x minus a squared, all the way up to some constant a sub n over x minus a quantity to the n, where n is the largest power of x minus a that appears in the denominator of a rational function, and all of the a's are constants which we will need to determine. So for an example, let's suppose we wanted to write down the partial fraction decomposition of 1 over x minus 1 times x plus 2 squared. We notice that in our denominator, which is already factored for us, we actually have two linear factors, x minus 1 and x plus 2. We notice that x minus 1 appears to the first power, and at x plus 2 appears to the second power. So when we go to write the partial fraction decomposition, we focus on one linear factor at a time. When we start with x minus 1, since it appears to the first factor, or to the first power, we only need to consider the first term of our sum here, a1 over x minus a. And so in our partial fraction decomposition, we're going to get a term of the form a1 over x minus 1. Here we do not need to go any further because our factor, x minus 1, appears only to the first power in that denominator. When we move on to x plus 2 squared, we notice that we have now a second term. And so here we need to include the first two terms of this sum. That will allow us to not only have an x plus 2 in the denominator, but an x plus 2 squared. And so we're going to add to this another constant, which we might just call a2, because it's the second constant in our equation, over x plus 2. And then we're going to add to that another term involving x plus 2, so maybe a3 over x plus 2 quantity squared. And then we stop because we have reached the maximum power of x plus 2 in the denominator. And so this particular rational function will have a partial fraction decomposition of the form constant over x minus 1 plus another constant over x plus 2 plus a third constant over x plus 2 quantity squared. Now for each quadratic factor, x squared plus bx plus c in the denominator, we have to include the following sum to the partial fraction decomposition. And this sum has a slightly different form than that for the linear factors. The form of this sum, each term will have a linear factor, b1x plus c1, over the original quadratic, x squared plus bx plus c. And we continue going up until we reach the power of that quadratic in the denominator. The big difference here is that our numerators in these terms are a linear function of x instead of a constant like they were for the linear function in the denominator. Everything else, though, remains the same. The number n here will be the largest power of that quadratic in the denominator, and all of the b's and c's are constants, which will need to be determined algebraically before we go to integrate our rational function. So for an example, suppose we wanted to find the partial fraction decomposition form for 3x plus 1 divided by x minus 1 times x squared plus 2 squared. Again, here we have a linear factor, x minus 1, but now we have a quadratic function, x squared plus 2, and that quadratic function is squared. So if we start with the linear term, x minus 1, we know that that will contribute a term of the form a over x minus 1. And that will be it, since it appears just to the first power. Now moving on to the quadratic, we have the quadratic x squared plus 2 as our factor. And so this will give us a term of the form bx plus c, some linear term, over x squared plus 2. But since it appears to the second power, we also will have some other term here. Say we could use dx plus e as our constants over x squared plus 2 quantity squared. And at this point, we stop because we've reached the maximum power of x squared plus 2 in the denominator. But here we have three terms in our partial fraction decomposition, one coming from the linear term x minus 1, and two coming from the quadratic factor x squared plus 2. Now, once we've completed all of these steps and have considered each linear and quadratic factor of our denominator separately, we then have our entire form for our partial fraction decomposition. The last step is to determine the coefficients, the constants in the numerators for each of the terms. We'll end this video by considering a simple example of this. So in this example, we want to find the partial fraction decomposition of the rational function x plus 5 divided by x minus 1, x plus 2. You might recall this rational function. We actually looked at it and wrote down the partial fraction decomposition at the very beginning of this video. But in this example, we want to see where that partial fraction decomposition comes from. So the first thing is we do notice that our numerator here has a smaller degree, which is 1, than the degree of the denominator, which would be 2 if we multiplied out those factors. And the denominator is already factored for us, and we have 2 linear terms, each to the first power. And so this means that we can write our partial fraction decomposition in the form some constant a over our first linear factor plus some constant b over our second linear factor. So a over x minus 1 plus b over x plus 2. And in order to find the partial fraction decomposition, we need to determine the values of a and b. Now what we're going to do to find them is we're first going to multiply through by our denominator. So we're going to multiply by x minus 1 times x plus 2. Right? And when we do that, a lot of things are going to cancel. On the left side, our original denominator is going to cancel completely since we're multiplying through by that denominator, and we're just going to be left with x plus 5. On the right-hand side, when we multiply this by a over x minus 1, the x minus 1s are going to cancel. And so what we're going to be left with is just a times x plus 2. Likewise, when we multiply this by b over x plus 2, the x plus 2s are going to cancel. And what's going to be left is just b times x minus 1. And so each of these terms, the denominator will cancel since the denominators are all factors of that denominator on the left-hand side, and we're left with this equation here. In order to solve this for a and b, there's a number of strategies that we can use, but one approach is to pick certain values of x and substitute them in, and we're going to be strategic in how we choose the values of x that we substitute, by looking at the factors that appear here next to the a and b. So for example, if I let x equal to 1 in this equation and substitute 1 for x everywhere, on the left side we get 1 plus 5, which is 6. We get a times x plus 2, which is 1 plus 2, so that would be a times 3. And we have b times 1 minus 1, which is 0. And so this is an example of a strategic substitution. We're multiplying b by 0 there. And so we end up getting the equation 6 equals 3a, which tells us that a is going to equal 2. Okay. Along similar lines, we could let x equal negative 2. And on the left-hand side, we're going to get negative 2 plus 5, which is 3. The a term will become 0 because we're multiplying a by negative 2 plus 2, which is 0. And we end up getting b times negative 2 minus 1, which is negative 3. And so here we see that b will equal negative 1. And so our partial fraction decomposition for this particular rational function will be our value of a over x minus 1 plus the value of b, which is negative 1, over x plus 2. And this agrees with what we had written earlier in our video.